Many thanks, Tom, and many thanks to the organizers, particularly Bartek, for this invitation. So far, a wonderful conference. And so I would like to acknowledge the work of my previous postdoc. He's not anymore postdoc of mine. He's now research fellows at University of Cambridge. And my PhD student, Rachel Mulungia, and lately the PhD student, Brendan Murray, who's here. He got interested in this topic, so he will be soon having some results. But the results I'm going to talk about now are mainly Lucas Mulungia and myself. It's very close in the spirit to what Thomas described today. Main difference is that I won't be very detailed on the numerical simulation part because that's mainly what Lucas did. And I will be, though, one more important point is that I'm going to talk about an exact solution of 3D Euler equations. It's not an approximation, it's not a numerical simulation without knowing the if there is singularity or not. This is an exact solution that develops blow up in a finite time. So it's a fantastic opportunity for us to enjoy and look at a real singularity. The problem is that it's not going to get the pot of $1 million, mainly because it's of infinite energy. So it's one of the coordinates, which is like equivalent to the phi coordinate of your talk. It's in this case is extended on the real line, and corresponding pressure is quadratic on that coordinate, so it's unbounded energy. But apart from that, if you thought for a moment that you could maybe put some boundary conditions about that mimic those fields, maybe in principle it will be possible to generate artificially such a finite time singularity. Okay, so let me talk about this. So the outline is basically. Well, I will be very quick here because it has already explained by Tom. But then these two topics which I have to discuss. There are two topics in this talk. The main topic that I want to discuss is a mapping to regular systems. So where I take the velocity field of 3D Euler that satisfies the 3D Euler equations, incompressible flow, and I map it non-linearly. I also map the time to a field where the solution is globally regular in time. So that's the first thing I want to discuss. And this process I introduced in 2011 with the idea of using it for improving numerical simulations. So the idea is that you do numerical simulation on the new system of equations, which you know will be globally regular in time, so you don't worry about potential singularities. And it's a bijective transformation, so you can go back and forth, and whatever you find in the globally regular system can be translated to the original system. The second point is trying to find an application of this, an application where I can show that this method of mapping is more efficient, gives more accuracy in a numerical simulation than just solving numerically the original equation. So I needed to find a case where I know the solution, right? Where I know at least some of the quantities that blow up, for example, and so I can compare errors. I can compute errors and compare. All right? So that's basically the story of this talk. So I will develop that in detail. Okay? So let me just first introduce to you the mapping, which probably very few of you know about this because it's very recent. This one maybe, well, I know some of you were involved in this, so I know. So, okay, I'm going to work in this notation, right? The vorticity equation for 3D Euler. Well, I put this just for completeness, but we're going to work with 3D Euler, incompressible. I will skip this part. I don't have any statement of theorems here, but I will I will tell you when something is a theorem. So like this is a theorem that Tom showed, that as long as this integral converges, we are sure that all the relevant superlative norms of the field are bounded up to time t and including time t. So let's talk about the mapping to regular systems. Here's the paper in case you want to get more details. The basic idea is I transform bijectively the time, so from t to tau, and I also transform the fields accordingly by rescaling the original field using the quantity that appears in the big AM theorem, in the big Kato-Maida theorem. Okay, and it's basically whatever appears in this integral will appear in this denominator. That's the usual story. When you do this transformation, you preserve the characteristics. So the particles equation for the particles, the motion for the particles in the x tau variables here will transform very nicely to the equation for the particles for xt variables in this context. So all the story. But automatically, BKM theorem implies that this mapped field is regular for all tau, because by definition, when tau is finite, this integral is finite, so everything goes nicely. But look at the advantage of the why are we doing this? Is because the equation of motion satisfied by the mapped fields, so in this case the mapped vorticity, which is the curve of the mapped velocity, satisfies basically the 3D Euler equation, except for an extra term here, which plays the role of a damping, like Ekman damping, right? But it is rigorous term. You have to compute it, and the expression is given here. It looks like it's basically the stretching rate hidden into these variables. Omega map is basically a vector that has maximum size equal to 1, because it is by definition omega divided by the maximum value of its modulus. So this is a unit vector because it's evaluated at the position of the vorticity maximum. So you have to follow that position and compute this. So this unit vector, so it's a sandwich between unit vector and the matrix of the gradient of velocity. Okay. So that's the form of the equation. So you see, it's easy to program an equation like that once you have the code for the original 3D Euler. It's just one extra term. The difficulty, maybe, it is a difficulty, is you have to be very accurate in finding this position of the maximum. So if you are in the case of Tom's talk, where the position of the maximum is fixed in time, you're very good, right? Yeah. If it's moving, it's a challenge, and we also try to tackle the challenge with changing initial conditions. So we tried all different types of things to see if this was robust enough. Okay? So why is it useful? For example, if you invert the relation between t and tau, you can compute the singularity time as a function of the vorticity maximum, or supremum normal vorticity, as you want to call it, in the original variables, but in terms of the mapped variables. I haven't provided you with a formula for this, but I tell you it's possible to compute because it's a bijective transformation. You can compute this quantity that pertains to the original system in terms of the mapped variables. So this is just an example. Of course, when you're doing a simulation, you end up generating small scales as usual, and at some point you will lose resolution because of that. It's always the same problem, right? You have only a finite memory. So this integral will cease to be, you cannot compute to infinity. So you have to model what's going on. But that type of thing is to be compared with prediction or assessment of singularity time using the usual approach of guessing a power law or something like that. Right? So, okay. So we can do this for 3D Navier-Stokes as well, because the BKM theorem also applies to this equation. You can also apply to MHD. The only thing you need is a BKM type of theorem, like in yesterday's Sakajo's talk, where you have an equation and you know that some integral of some functional of your field, if this integral is finite, then you can show that all the other of the relevant norms are bounded. That's all you need to construct this transformation. So the problem is that all these cases we don't know a solution to compare with. So the idea is to find an example where you can really use previous knowledge of solution. So we looked at this interesting suite of results, starting from the theory by Gibbon, Focus, and Doring. Charlie, are you? Yeah. So, well, I'm going to talk more about that in the next slide. And then the idea is to basically to get this analytical solution as accurately as possible with arbitrary precision, and compare with the results of numerical simulation from both original system and mapped system. Okay. So these two papers are just came out from our group, so 2 JFMs. Actually, these rapids took longer than this one to be adopted, but something should happen. So the topic 2 is the stagnation point type solutions of 3D Euler, and I hope this is interesting to you. It's really, for me, it's there's a lot of information to take away from this. I still don't know completely all the details. In particular, I don't know how to explain the spectrum, the energy spectrum, or I don't know how to compute analytically that. I can compute maximum vorticity, maximum stretching rate, and so on, but I don't know how to compute the spectrum analytically. So, just to give you a motivation, these are 3 examples. So for the non-experts, would be this was, well, first by order, right? So this was Cowan Lee, 2006. I just basically want to show you that people are using discrete symmetries all over the place, right? So mirror symmetry, as Tom was mentioning. This was the paper 2008 with Kerr and myself. Another set of symmetry planes. In fact, there are several symmetry planes in this case. And this is the more symmetric case. In fact, it is shown only the fundamental domain. So all these faces are symmetry planes, somehow. So there are 6 symmetry planes in Taylor-Green, Kidapel 6 symmetry planes, Kerr's type of vortices, 4 symmetry planes, and the simplest case is 1 symmetry plane, but if you're doing periodic boundary conditions, it will be 2 symmetry planes automatically. So, but we don't want to do periodic boundary conditions. We just want to do these solutions of Gibbon, Focus, Doring. In that case, we consider the 1 symmetry plane only, and the situation is like this. So this is the exact solution of 3D Euler via a 2.5D reduction. So I write a representation of velocity field with 2 components in the horizontal direction, depending on x, y, and t. So x, y are my horizontal coordinates, and the ux, uy are horizontal components of velocity, and the vertical component has explicit z dependence. It's linear z dependence. And the factor in front is a function of x and y and t. This is not the most general solution, but I stay with this one because it is enough for me. Yeah. So incompressibility leads to the following condition, that the horizontal divergence of this 2D field has to be equal to minus gamma. So basically we're going to a 2D model where which is not incompressible, right? The symmetry plane is z equals 0, as you can see, because it changes the sign of the z component of velocity field, but not the sign of the other 2. So it's really a mirror symmetry plane. And the x and y coordinates are chosen to be in periodic domain. Correspondingly, if you compute the vorticity of this velocity field, you get a more messy expression, right? You get z times sort of the perpendicular gradient of gamma, and you get in the z direction the vorticity just this scalar, which we will call scalar vorticity. So basically, you have vorticity as a function of derivatives of velocity, and you have gamma, which we will call the stretching rate, as another combination of derivatives of the horizontal velocity. So this means that the horizontal velocity can be obtained, right, by Helmholtz decomposition in terms of gamma and omega. The zero mode, you can put it to zero. Okay, so that's the good thing. Before writing any equation, this representation is telling me depends on two scalars. And these two scalars are 2D. So that's why this is called 2.5D, because it's really 2D, but it has some extra. Yep?
Do you know about the analog to the shallow water equations? Because so far we've done is exactly what we do in a shallow water problem, where you take the vertical velocity proportional to z, but then there's a free surface, and then it's different after that.
Yeah.
There is a decomposition for the two-dimensional shallow water equation.
Yeah, well, I'm not completely, but yeah, sure. If we can extend these solutions to these other problems, it'd be fantastic. Yeah. So now comes the equation, okay? So just to remember, right? This is the u, the full 3D velocity, and this is the full vorticity, 3D vorticity. So the velocity equation, just momentum equation, really. If you take the z component, you just need to take z gamma, right, in this part. So use the z component, z gamma here. There's a bunch of terms here, but this is where you take the z component, right? So you get several terms, and it all adds up to this, right? And times z. And on the other side, you get minus p comma z. I'm being a bit, I want to be detailed here because it's nice to see how you get this solution. Okay, on the other hand, if you take the vorticity equation and you take the z component of vorticity equation, you immediately get this nice equation that tells you that vorticity is being stretched. And that's why we call gamma the stretching rate. Okay? Okay, now from this equation, you can solve for everything, because you can solve for the pressure by integrating in z. And you find this expression here. So this is the integration constant of integration that depends on x, y, and t. And then you have this quadratic part. And then the coefficient in front, due to a nice topology condition, it has to be equal to the average of gamma squared over the plane. So it's a condition you cannot avoid. Similarly, if you now take, once you find the pressure, you take the derivative of this equation with respect to z, you find an equation for gamma, an evolution equation for gamma. Right. You may wonder what is the equation for pH. That's the homework. Anyway, basically, it's just, again, go back to this and the other components, you will find, no problem. Let's consider now, let's focus on these two. You see, remember I said omega and gamma determine the velocity field. Now, we have two equations for two unknowns. It's completely closed system. So, here we are. Oops, sorry. Okay, so the summary, you have one equation of motion for vorticity, one equation for the stretching rate, and this definition. And then you have to use this transformation to go back and use the advection. So that's our system. Question is, well, here's the statement. This system blows up in a finite time, and we can compute analytical solutions for the blow-up quantities, not for everything. But so, interesting story. After this was published, or during, given one of the authors, and Koji Kitani, started a simulation of these equations they didn't know there was an analytical solution. So they did simulation and found good evidence of finite time singularity, even computed approximate value of the time. And at the same time, Peter Constantin found analytically the procedure to demonstrate the blow-up using a method of characteristics. So it was completely closed. Two fronts working, and then nothing happened after that. 15 years after, we're here. So one of the important things, even there was a work done, published a bit later, but done during that time, by Gimon and Gitani again, where they find a criterion more general for MHD models, but they find basically that if this integral is finite, then all the norms, the relevant norms are bounded. So a BKM type of criterion, perfect for me. Because now I can do this transformation and compute my equations. So I define the mapped time in this way, as you see. It's an integral. And normalize. Normalize dividing by the maximum stretching rate. This is not the maximum vorticity. It's the maximum stretching rate. The vorticity, I also define it. The mapped vorticity has to be, right? All the fields have to be divided by the maximum stretching rate. The equations become basically the same as before. All the black terms are the same as before. Oh, sorry, this lambda is from some model I have introduced. Please imagine it's equal to 0. Yes, you have a question?
That omega is the reduced omega, right?
Yeah, it's the that omega is the scalar omega.
On the right-hand side, that the reduced omega.
It's the scalar omega. Yeah, it's the scalar omega. Yeah. So gamma and omega, gamma little omega are the scalar fields that determine everything. Yeah. So sorry for this step. But if you are interested in the lambda models, you can look at the first JFM paper in 2015. Sorry. So you see, focus on the blue terms. It's very similar in structure to what happened in 3D Euler. You have a time derivative of this quantity is equal to the quantity times something. And what is here is a uniform function of time. So, sorry, uniform function. It's only function of time. It doesn't depend on x and y. Okay, the same in this is the same quantity here. This sigma is just a sign. It's plus or minus 1. It's a bit technical, so I won't explain. But don't worry about it. Just take it for the moment equal to minus 1, and it will be fine. Okay. So now I'm going to explain the analytical solution because now you know the equation. This is the equation for the mapped system. You know the equation for the non-mapped system. So you know everything, and you know how to do numerical simulation. So that part is easy. We will do it. Let me now focus on the analytical solution. Okay. So using Lie symmetries in the normal direction to the plane, interestingly, I have to use the 3 dimensions to solve these equations. So you saw the equations are just two-dimensional equations for gamma and omega. You would think that to solve this equation, you don't need to go to 3 dimensions. But the way my method works is I write a Lie symmetry for the system, and then I integrate because I have a lot of Lie symmetry, so I can compute the commutator and find a lot of conservation laws. So, but I need to use symmetries that go on the z direction. So after a miracle happens, after the work, you find solutions along characteristics. So characteristics are basically the x and y in the 2D plane that follow the velocity, the horizontal velocity, okay? So you can find solutions along characteristics, this is x and y of t, in terms of the initial condition of your trajectory, okay? And this A satisfies some ODE. Again, if you're interested in more details, I can show you later, but I didn't want to show this time. It's fine ODE that depends on the initial condition only. And so you can easily integrate it if you have a good if you have a good package. So it's really not a problem of solving a PDE. It's ODE. Okay. So
are mapped in the form of x on y.
yeah, exactly. And they follow the derivatives. And what happens is that this factor that is here is the one that will produce the singularity, because this integral is going to grow. And when gamma, and when your initial condition is at the point of negative value of initial condition gamma 0, let me remind you that gamma 0 is the divergence of, it's minus the divergence of the velocity field. So the integral over all the plane is equal to 0 by definition, because of periodic boundary conditions. So gamma must have, unless it is 0 everywhere, must have a negative value. So like in the visited burgers. So then the infimum, so the point at which you have the infimum of gamma 0 is the one that dominates the singularity. And it goes like 1 over t and so on. So you can explain everything. And the part that, so asymptotically you know what's going on, and this function a determines correction to the asymptote. So it's very simple. Okay. So the initial data taken by Okitani and Gibbon was quite simple, the same function for the two gamma 0 and omega 0. But as you see, the singularity depends only on gamma 0. Well, I didn't show, but the equation that A satisfies depends only on the initial condition in gamma. You can, after some computations, obtain explicit formula for the blow-up time in terms of the integral of the elliptic function of the first kind. So there you have to do numerical massaging, right? So you have to do Mathematica, for example, and get as many digits as you want. So that's basically the story. But the asymptote is very simple. The infimum of gamma goes like minus t star minus t to the power minus 1. You can demonstrate this. Okay? So let me show you some results of the numerical simulation. We're going to use CUDA, FFT, and GPUs, of course, House the aliasing filter, and Rijikuta fourth order for time stepping. And these are results of 3 resolutions, 256, 512, 1024, squared, obviously, the plane, right? And this is a plot of, as a function of time, of the numerical solution of the original system of 1 over maximum stretching, or minus 1 over the infimum is the same in this case. It goes, well, look, this is the time 1.3, so this is already looking at the asymptote, right? It goes nicely as a straight line and hits near the singularity time that we computed analytically. But isn't it interesting that the 3 curves are falling in the same place? Because that's not what you expect. You expect some convergence, but not so fast. So something interesting is going on here. Some animations.
Yes, that's right.
Sorry?
Did you try lower resolution? Could you break it?
Yeah. You can go very, very low without problem. Yeah, but I give you more details about that. Let me show you these animations for the moment, so you can get an idea on the. I hope it's working. Yeah. So. This is stretching, this is vorticity. It's not, so the plot is basically, it's hard to manage the color code for this plot, so we decided to put constant values. So when you see these holes, it means that it's getting really, really low. This is the infimum. It's going to 0 very fast, okay? And it's going to go 10 to 16, kind of, 10 to 14, okay? And when it goes infimum very big, right? Vorticity goes to 0. So it gets expelled, because for negative stretching, vorticity doesn't concentrate. All the contrary, it gets expelled. So it gets pushed to these regions. Right? So notice that the initial condition is kind of nice. It looks circular, but it's not. I mean, the initial condition looks circular. After a while, it is not circular. You can see there's a kind of twisting. There's a kind of helicity. It's very interesting. And you see the time here, 1.4. Yeah. All the interesting things happen so close to the singularity time that this typical way of looking at the thing doesn't give you any information. You have to go to the mapped system, where you map the time so you can really go as close as you want. You will see now what happens. So in terms of figures, this is from looking at the snapshots, that's all we can do. We need to look at other things, right? So first of all, let me convince you that comparing errors, right? Because that was the first idea, to see that the two models are, to compare the two models to see which one gives better accurate results. So we're going to look at basically the two equations, but using the same spectral method, we try to be very fair in all these comparisons. And even the problem for the mapped systems, you have to get an interpolation to find the maximum stretching. So it's a problem, you could say, it's a challenge, but it still gives better results. So there are three formulas I will show here, which give you the maximum stretching rate as a function of time. One is the exact formula, I call it exact, because it depends only on the initial condition, and I can compute it with accuracy, arbitrary accuracy. Depends on my mathematical code, right? That's exact. This is the usual thing you would do. You would just take your field in the original system and compute at the maximum. That's another way. And the next way is a little bit difficult. I cannot explain now, but based on a nice equation that is satisfied by the maximum stretching rate, you can find a formula. I told you this is a bijective formula. From the data, numerical data, from the mapped system only, you can compute these integrals and obtain the corresponding stretching rate of the original system. So it takes time to find it, but you know it's bijective, so you can find it. That's the point. So all this will be compared. We will use Simpson rule to do these integrals. We will use the usual finding the maximum interpolation, for example. And this, as I told you, is exact up to any order. So I define, for example, this error, which is normalized, so it's between 0 and 1. When it is equal to 0, the two functions are equal. And when it's equal to 1, the two functions are very dissimilar. I compute this error as a function of time for several runs, right? But this is the error this is the result for the original system. And as you can see, initially it's very small, 10 to minus 16. But then it grows and grows and grows and grows until it takes the value 1, which means it is a bad solution after a while. And this is in tau variable, sorry for that. It corresponds to t near t star up to machine epsilon. So it's a barrier of the original system. When you have a computer with double precision, you cannot go beyond the number. Even if you try to trick the system by adding small numbers and so on, it won't work because the errors start developing much earlier. So it's an iterative problem in the system. However, in the other case, using the mapped system, you get a bit of errors initially by a bad luck. We cannot reduce these errors too much. We will need to reduce a lot the initial time stepping. But don't worry about those errors because eventually, where it matters, the errors do not accumulate. And you can see it remains below 10 to minus 10 until 40. So this is beyond machine epsilon, and it will continue to the order building. Fantastically. So, okay, let's see what happens. We can get close to singularity incredibly to tau equals 500, and we kind of got bored of continuing the integration. And this corresponds to t star minus t 10 to minus 140. Imagine how close can that be. We can be even better if we had more patience, right? Now we can check. How do we know we are doing the right work? Well, we have a formula for this proximity to the t star in terms of the maximum stretching rate. And we can use this formula to compute numerically some extrapolation. So we extrapolate from the data, and we compute numerically this integral. There's a lot of error in that. So 5 minutes? So, you have a question? No, sorry.
How do you know that the T 10 minus 140 it is really reliable? Because you use the numerical solution in place to get your maximum, right?
Yeah.
You need to use the solution to compute the gamma maximum.
Yeah. So
How could that be?
we have an analytical formula for T star minus T. Let me show you the next. So we have an analytical formula for T star minus T as a function of tau. Okay, in terms of Lambert function, this is a asymptotic formula, but it's very good. So we use this formula, and we compare with the result of our numerical simulation by extrapolating this integral using the numerical simulation. So you expect a lot of errors in the extrapolation. However, it works fine. So there's a little bit of detail here on how we extrapolate. We have to use a kind of a guess function. It's not a power law. It's a combination of a constant plus a power law. But it's only two parameters that we fit, nothing else. So we do that, and we can compute the error between the numerically computed proximity and the exact value of proximity as a function of tau. Would that be explanation?
The point is that when you pick that, the error involved there could be much larger than what you have.
Yeah, exactly. But it's not. I mean, the absolute error, maybe, but the relative error is small. And that's what we're looking for in this case, right? So we compute the relative error of the estimate for this integral and against the actual value of it from analytical formula. And we find that you have to read this thing backwards, right? You have to go, you go this way closer and closer to T star, and this way larger and larger in tau. So we find very nice convergence, and it goes below 10 to minus 7. So this is a, as I said, relative error, right? So there could be an error, of course. It's a very small number, right? But the relative error is quite small. So we're quite happy with that. We have other ways of comparing, but I didn't want to show more. We also compare, for example, the L2 norms of the quantities. So we get the similar results. Okay, so let me talk about physics now. What's going on in this system? Until year 2000, so when Gitani and Gibbon did the simulation, this is our simulations, but this is basically the same as what they got. They reached up to 256 resolution, and they found the same results that we found. We went to 4,000, but it was not necessary, really. Could go to 256, no problem. It's the same result. Initially, well, sorry for the change of scale here. So remember, so this is 500, so it's here, right? So this, look at this magenta line, which is the main quantity to look at. It's the energy, well, it's not energy, it's the spectrum of stretching rate squared, right? So it's not energy spectrum, but it's equivalent to energy spectrum, if you want, for the quantity gamma. So it goes like this. It's a very nice fit. You can fit like this with the typical exponential decay. And you see, this is ln log, so you see a straight line, you're happy. And this is what happened until 99. You're very close to the singularity time, 0.0002, and you see this. So you think it is the usual singularity. But if you continue beyond, you can still, can still be done with using the original equations integration. But then to 100, 200, 500, only with the mapped system. And what happens is that this thing that appeared very important, the usual thing, with delta going to 0, suddenly this is dissipated somehow and gives rise to a large scale build-up of another type of spectrum, which looks Gaussian. So this is still consistent with the singularity. The problem is you have to measure this delta now. It goes below, basically you're looking at me like that, right? You're looking at me like that. It goes below round-off error. What can we do? This thing goes below, disappears from the radar, basically. So that's the way, yeah. But then what it leaves in the wake is this thing that's built up itself. So just to be sure that this is correct, we tried to check this fit, right? Computing n of t, c of t, and delta of t, and using very classical Sobolev inequalities for the maximum of gamma in terms of Sobolev norms of gamma. And we found that these inequalities are always satisfied, and in fact, they saturate, which is very good because we know, well, this is a work I did with Mark Brache first, when we did a simulation of the Taylor-Green in 2012. We found that the duration of these inequalities corresponds to a spectrum that is isotropic. Remember, we have two dimensions here. So it's when all wave vectors, doesn't matter the angle, they share this kind of the same energy, right? But the energy depends on the size of the wave vector only. That's it. Yeah. So this is the analytical formula, delta of t. So for those of you who don't know, this is called analyticity strip width. And you can use this working hypothesis for the spectrum and plug it into these Sobolev inequalities and find the saturation value, and you find this formula. So please believe me, but it's in the paper. So delta of t goes like the square root of pi over tau. Tau is the mapped variable. So you can see here, this is delta of t computed from the fit, and this is tau, and this red line here is the theoretical curve of the saturation. So the inequality says that delta has to go always below the curve, which seems to be happening, and it converges nicely to the curve. So it's very nice, because now this means that this is not crazy, right? That this is kind of okay. But what is interesting is that we believe, really, that this is the asymptotic regime, okay? We cannot prove it, but it's kind of, I mean, we could continue integrating and maybe one day something will happen, right? Now, believing that this is the asymptotic regime, and then you want to compute when you will reach the smallest scale, right? When you lose resolution, it will occur at tau equals 20,000. So here is 500, so tau 20,000, or in terms of original time, proximity of 10 to minus 9,000. And this is in resolution 512. So answering your question, Colm, you should do this in resolution 10 or 16. It would do well in terms of this parameter. Okay? Yeah. Yeah, well, I was just exaggerating. But it's basically, we're using too much, and we can use, so why not? I mean, it's not a lot for a computer. Yeah? So?
Not so many people compute like what a sheet singularity, like Marshall used to do. It's extremely difficult to get the solution with delta. I don't know why you can claim that such a conclusion. It's not difficult to get a equation in delta.
Yeah, I don't know. I mean, this is the first time we got it.
I was looking to get the accuracy of delta.
Yeah, we found this thing, we didn't know what it was. And we tried, okay, let's try to fit it with something, right? So it's a fit. And in fact, you can think of it in a more advanced way as instead of putting this sign here, this twiddle, you can rigorously work, you can define a working hypothesis saying, okay, the spectrum is less than or equal than an expression like this. And what do I obtain, assuming that?
Do you first compute numerically the energy and then try to fit it, or you do it differently?
Yeah. We compute this spectrum like that, as you can see it, plotted here, right?
And then you try to fit the delta from that formula?
Yeah, we basically, we fit everything, delta and n. We fit here. And the nice thing is that it starts at larger scales, so it's no problem of resolution. Well, that was the previous. That was here. That was the burst of energy only. It was a transient state. It went down the round of error. Well, you're talking about. You think these numbers are too small? No. Well, it's the double precision. It's double precision, yeah. But you know, when you compute a spectrum, you square it, so you're fine. This is the round of error, really. This level here. Okay. Yeah. I cannot say much more about the simulations, but say, for example, we had another technical problem, which was an inverse cascade. So we had to kill this inverse cascade with a little bit of hyperviscosity. It was a technical problem, so that's why you see all these curves. Yeah. So okay. So I think that's this story. So just conclusions. So so we find basically that the numerical integration of mapped regular system leads to more accurate results at very little price. So it's a very interesting tool that I would recommend all of you to try to use if you're doing some simulation. If you know there's a BKM theorem, try to use it. So we get unprecedentedly close. This is a record, a world record, Guinness. And it's a cautionary tale for 3D Euler, because you think you know what's going on with the system, and then suddenly it changes to something else. In the case of Taylor Green, for example, as you know, Mark Rachet, 83, and so on, they thought it was exponential decay of delta, but then suddenly it seems to be accelerating. So it's a question now, what's going on? So yeah, ongoing work is on full 3D Euler equations, where we have to apply all this machinery. So it's more difficult because we don't have analytical solution to compare with. So I invite you to look at the simulations, and if you have not watched this movie, this is a great movie. Singularity Day. It's a short film, it's 3 minutes. It's on YouTube. Just put this in the search, and you will find. The Singularity Day is a great idea because I don't think, because a lot of people have seen it. Who has seen it? Yeah, no. Unless you want to see it.
Yeah, let's see it.
Yeah. Okay, thank you very much. And this is at least I know a lot of papers are not here. Okay, you can look at this paper at the first of the JFMs, and you will find the very recent references. So sorry if you are not here, but I tried to put in red all the people that are in this room. So Howe, Kerr, Bustamante, Doring, Ayala, Protas. Yeah, I think. Sorry if I missed one. So thank you very much.
The math system and what you're going to the demo case, not your
yeah. There?
Yeah. This beta of tau.
Yeah.
You need both systems in order to get that.
No.
If you look at the equation for the map, you can determine beta.
Yeah.
So it says here the position of the map vorticity maximum.
Yeah.
In the map, in terms of mass area, beta is determined just in terms of mass area.
Exactly. Yeah.
You don't need to know the reference.
No, you don't need to know. No. Yeah. Exactly. Yeah. And in fact, if you want to really more detail, for example, to find this in terms of the mapped variables, you need to take the ratio of the mapped energy, so-called, like the integral of mapped velocity squared, divided by the original energy. So the mapped energy is not conserved, but the original energy is conserved. So when you take the ratio, the square root of that, you get this this omega. So you can use that. Yeah, sorry.
You mentioned that it's possible to use this idea of the mapped system as long as we have some quantity of interest, like a EKM here.
Yeah.
To do the same for now yourself, where you have now the entity instead of the entity.
Yeah, you can do for so you the same. It's the same quantity as far as I understand. I was taking a look at the BKM paper last night, and it's the same quantity that you use for Navier-Stokes. That's what they say. But it's a bit more difficult, the transformation, because you have the velocity, and it will not scale as nicely as this. So you have to write down an ODE for the viscosity. But you can do it. I'm planning to do it. So if you are interested, we can discuss. Yeah.
I have a question. I'm not convinced that by making this change variable, you can get better, more accurate solution, in my opinion.
Well, not always. I mean, we have done several tests because we don't know why in general, right? It happens, right? But we've done tests on.
You just scale the solution in by constant, basically, right? By constant time, not changing the spatial structure.
Yeah.
The map solutions not become more regular in a relative sense. There's more. If you use a uniform mesh, you're not going to resolve the singularity better. The map system.
Yeah, exactly. So you're gonna hit the resolution, the smaller scales. You're gonna hit the smaller scales eventually, even in the mapped system. And something, sorry, I forgot to mention, is when I compare the original system with the mapped system, I do adaptive time stepping in the original system. I adapted using this formula. So delta T is defined in terms of constant divided by maximum vorticity. So I'm really fair in the comparison between the two.
No, but it's really the spatial resolution.
No, spatial. No. I know. Spatially speaking, you will hit at some point the smaller scale, unless this miracle of this initial condition, of this 3D solution, stagnation-point-like solution, which takes so long to get to the resolution limit by chance. But any other system we have tried, you get there in a finite time. You get to the small resolution in a finite time.
The original system under the result in space, the map system will be under the result at the same time.
Yeah.
So you're not going to gain any better resolution in space.
Yeah, sure.
Why you can, if you're under the result in space, no matter how well result you find, the whole thing will be corrupted.
Yeah, you will get basically the same order, right? The difficulty, the problem will appear at more or less at the same time. But you gain a little bit extra. So you can get a little bit extra with this new method in those cases. And that's what I was trying to show, because originally, finding this transformation that, that could leave me so close to the singularity in the case of the stagnation problem is that...
If you have a result in space and also time accuracy is kind of minus 900 or whatever, I don't really make sense.
I am explaining to you, if you use a system that will eventually, in finite time, hit the smaller scales, then you are, in both cases, I agree with you. Yeah. The only case where this was different was the stagnation type solution, where you never get to the loss of resolution until very, very, very late.
But let's discuss it.
Yeah.
You have a basically OD type blow up with looking spatial field, this particular.
You have to diminish the field, right? It's not. Yeah, it has to. It's a reduced 2.5 dimensions. It's not like the OD you have 2.5 real dimension.
No, I mean, like, some of you make these equations, blows up the OD type blow up.
Yeah, it's true.
need a doubling amplifier to resolve this in space. We are leaving one out of time.
Yeah, thank you. Thank you. So.